this, and so on. So it'll be somewhat condensed and only semi-formal. So we're primarily concerned with digital signal processing here. We're not talking about analog things. BCI is mostly a software story anyway. And so DSP is about systems, which are also known as filters, which transform one signal into another. And there's a special class of systems that are so-called linear time invariant systems, which cover things like spectral filters and so on, and the optimal design of these spectral filters. And that is one of the best developed areas of signal processing. So this is where it really shines, and which is most of the reason why you want to have signal processing in a brain-computer interface. There's also other areas such as statistical signal processing and things like adaptive filter theory and so on, which are among the rather advanced areas of signal processing. That includes things like the Kalman filter, which is well known, and recursive least squares estimation and various kinds of adaptive estimation. And so that goes a long way towards efficient design of certain kinds of solutions that are useful in brain-computer interfaces. And there's a rather new topic that's sparse signal processing, such as that includes things like compressive sensing and sparse recovery, which is a rather new topic in signal processing the last 10 years or so. And it does have applications in BCI. It's one of the most sophisticated, you could say, things that you can do. And we'll touch on that in one of the later lectures. So there's several sub-branches and concerns and so on, and there's overlap with machine learning and statistics and so on, as you see. And we'll start pretty much with the basics now. And so we'll say you can view a signal like this x of n here as a mapping from an index set, such as integers or discrete time, onto vectors. That's samples. Vectors in the case of multi-channel signal, basically. So that's what it is, and that's how we write it. And from the point of view of signal processing, BCI is a system, and it transduces the input signal, say, let's call it xn, which could be EEG, into a control signal. That would be the output that goes to the thing that you want to control, for example. And so any such system can be defined by a transformation rule. You say, so you have this input form xn, and you have a rule that turns it into a new form yn, and the rule can implement, have some mathematical form, basically, to be able to formalize that. So I'll give you a few examples of that and a few definitions. I just rattled these off. But it's useful to know them. So you can say a system is, I'll be quite literal here, a system is called static if the value yn, the output value, at any sample n depends only on the input value xn for that sample. So you're not transferring information across time at all in there. Otherwise, it's called dynamic. A system is called causal if the output yn at a given time n only depends on values xm for m smaller or equal to n. So it does not look into the future in a sense. Otherwise, it's called non-causal. And so if you build a BCI physically, obviously it cannot look into the future, so it has to be causal. And then a system is called time invariant if yn equals a transformation of xn such that if you shift the time, relabel it in a sense, the output is the same, is basically, the shifted output. So the signal is not, the description does not explicitly depend on time. Okay, otherwise it's called time variant. And lastly, a system is called linear if this equation holds, which means under scaling and under summation, the scales and summations propagate through the transformation rule. So twice the input signal gives you twice the output signal, for example, and the sum of two input signals gives you gives you the transformation of the sum of these input signals. Otherwise, we call it a non-linear one. So basically, the transformation rule is a linear function of the inputs. And it's quite remarkable how much you can cover with linear systems. So that's already sort of almost the entire story on definitions. It gets a little bit more interesting now. So when you now say, let's view a BCI as one of these filters, the whole thing, you would say, well, first and foremost, since you run them in real time, they have to be causal. Okay. Basically also means that any of its parts have to be causal. Also, usually they do some kind of a temporal filtering. I'll talk about that. So they do transfer information across time in a sense. And so they are dynamic. Many of them are time invariant. So, you relabel time and the output doesn't, isn't affected by that. But there's adaptive BCIs which are not. And also, some simple BCIs can be linear. Certain kinds of, say, just for the BCI experts here, linear regression on EEG is basically linear. And there's one more quirk, and that is usually you don't need the output of a BCI at, say, 1 kilohertz. You need it maybe at the screen refresh to partition it into things which are very well described by signal processing blocks. And so that partitioning gives rise to certain kinds of filters that play a role in BCIs that are prompted by these original definitions.